my gosh, it's working. Okay. We weren't in high enough quality. Got it. Nailed it. Okay. All right. So if you are jumping on to watch this live stream, we're going to get started in a minute. But luckily this is working again, so that's a win. So just give me a couple minutes and then we'll get started. Okay, so I know we're running a couple minutes early, but we're going to get started right now so that you guys can get out of here. And if you are watching later, that's totally fine. It's just less you have to fast forward through. So one of the most requested topics was to talk a little bit more about slope fields. Slope fields are something that are not particularly difficult, but for some people, they're just the thing that we haven't really spent any time on thinking about them because there's been much more difficult things to think about. So we are going to think about slope fields today and just do a quick little crash course on them. If you want to chat with me at any time, you can either use the YouTube live chat bar. You just need to be logged into your YouTube account, or just feel free to send me a reminder, and that will work just as well. So, quick crash course on slope fields. If you have a function, and this is just the original function, this is not the derivative, but I'm looking at y equals x squared minus x at x equals 2. If we zoom in close enough to that graph, on a small enough interval, no matter what curve you look at, it's going to appear what we call locally linear. And so this property of local linearity is something that comes up a lot. If we look on a small enough scale, we can really approximate any curve by using a locally linear piece, or any differentiable curve at least. So dy dx at that particular point would be whatever the slope of that section would be, right? That would be your slope there. Now, I could continue to do that for other points, right? So here I've got all of these values at x equals 1. I've got all of these values at x equals 0. And so if I continue to do this, I wind up with a field of all the slopes at every various point. So that is really what I'm looking at when I look at a slope field. I'm looking at the collection of all possible slopes that fit the constraints given by a differential equation typically. So a slope field shows small pieces of the tangent lines of the original function of the solution curve. Since we know the tangent line is a good approximation, the particular solution should not differ much from those segments. So when we get a slope field, we are looking at the family of possible solutions. From that, we can come up with one particular solution, and typically we would be given an initial condition to draw that through. So for instance here, I've got my family of slope field curves, but then I have this particular solution that's drawn through it. And so I might be given, say, an initial condition at that point, and that would help me find what is we usually call our C value, right? But figure out which particular curve we care about. So one of the things that we're going to talk about is this quick word, which is an isocline. That is the all of the points where a solution has that particular slope. So quick tips when we look at slope fields. First one is to look for isoclines, especially nullclines. So again, an isocline is any point where a slope field has a particular slope, but a nullcline will be any point where a slope field has a slope of 0, right? Null should make you think 0. So in this particular case, I have an A and a B. One of the following is for dy dx equals x plus y. One of the following is for dy dx equals x minus y. And so what I'm looking at here is, okay, well, what values would make these equal 0? So x plus y would equal 0 anywhere along y equals negative x, because anywhere on that line would fulfill this condition. So if I look at these and I see that I see 0 slopes everywhere along this y equals negative x line, that's a nullcline, right? An isocline for 0. And so this is going to be the one that's dy dx equals x plus y. And I know that because along y equals negative x, or whenever y is the opposite of x, we have this condition of the slope being 0. Now for this one, if I'm looking at this, now I'm saying, okay, well, x minus y would equal 0 anywhere where y and x are equal, right? So that would be where my null line would be for that. And so if I look along the line y equals x here, that is my null line for that. And so this is dy dx equals x minus y. Since typically a lot of what you're doing is you're trying to take these and match them to other things, that is a pretty good idea of where to start, is to look for those isoclines or for those null lines. Now, if you're drawing it yourself, you can also say, oh, anywhere along that isocline, you will have a slope of k, and then it makes it easier to draw the slopes in because you know some patterns. So let's look at this one again. So given this differential equation, we've got the slope field already, and again, you could come up with that just by plugging in points. But where would we expect this slope to be 0? So let's look at it. Here's my equation for the slope. Let's just set that equal to 0. And so this would equal 0 anywhere that y equals negative 1/2 x. And if I look at that, that line is right there. That's where you have your slopes that are equal to 0. So you can look for those 0 slopes, right, along that isocline, and that will give you those points. So a really good way to make sure that you're understanding those. Now, drawing the curve that goes through the point 0, 1. So 0, 1 is about here. And so I'm just going to estimate slopes around that. So right around there, that would be my slope. And then if I follow that slope up, it's going to get a little steeper and a little steeper. If I follow that slope down, it's going to kind of approach 0. And so you can start to sort of estimate what your slope would be around that point. So isoclines, null lines, a very good way to start drawing these. The next thing that I would look at if you're looking at slope fields is dependency on one variable versus two variables. And the way to really look at this is if you look at your values, what is making it change, right? So let's say that I look at this one, and I'll tell you they told me one of these was only dependent on x, and one of these was only dependent on y. So here's sort of how I look at it. I would look vertically at one sort of row. Let me make my highlight a little smaller so we can zoom in a little bit more on this. So vertically along one row. If I look at that, notice that the x value doesn't change, is equal, right? X value doesn't change, but the y value does change. And so I can tell here what this is dependent on. So at every single point along this curve, along this vertical line, our slope is the same, which tells me that the y value does not matter, okay? If the y value is changing, but the slope never changed, so this does not depend on y. Because the x value doesn't change along that line, and my slope never changes. The y value does change, but my slope still doesn't change. So then you can kind of look at it going the other way, right? You can look at it going the other way, which would be to go this way. And so notice that even though along this, your y values are the same, right? Your y values are all the same, but your slopes are still changing, which tells me again that this depends on x, because as the x values change, the slopes change. So this one here is only dependent on x. This one only depends on x values. And so that is something that can help me match it, because sometimes my answer choices may only have an x value. So in this case, since this only depends on x, I can say, okay, well, this is dy dx equals 1.1 x squared. Now, again, there's more things we can do with that, but in this case, that's where I would start, is that we have this only depending on our x value. Same thing goes on this one to the right. If I look at any particular row, notice that the x values are the same in that row, but the slopes are all different. So I can say that this one depends on y, because as my y values change, the height change, but as my x values change, they don't, or the slope changes, sorry. And so this would be dy dx equals 1.1 y squared. So looking at whether it depends on one variable, two variables, or both is really important. Now, if we looked at something like one of these that we did before, if I look going this way, my slope changes along every x value, and going this way, my slope changes along every y value. And so that's a time where I could say, okay, dy dx actually depends on both x and y. Okay, couple more things. This is going to be a short and sweet live stream. So, patterns by quadrant. This is something when I match that I use quite often because knowing what the patterns are based on the quadrants can really help you. So, in the first quadrant, remember that your x is positive and your y is positive. And so when you're looking at this, that should sort of help you with your slopes. In this quadrant, you've got positive, negative. In this quadrant, you've got negative, positive. And in this quadrant, you've got negative, negative. And so I can start to make judgment calls about what my slope will be just based on that. So, like, if I was using this equation, I see that I have negative xy, or x over y. Anywhere in the first quadrant, this should come out to have a negative slope. Anywhere in the third quadrant, this should come out to have a negative slope. Because those are the places where you're dividing x by y, and where those would come out to be positive values, and then you're switching the signs. Now, because x and y have opposite signs in these quadrants, and then you're making it negative out front, those should be the quadrants where you have a positive slope. So looking at this, I know to make the graph, I can just plug in points, but at 1, 1, this will have a slope of negative 1, versus at negative 1, 1, this will have a slope of positive 1. And you can start to sort of match things up that way, right? You know this will be similar, that will be similar, and you can start to make judgment calls when you're matching based on the quadrants. This also works based on, in trig what we would think about as quadrantal, but on values that are right along the x and y axis. So in this particular curve, anywhere that y is 0, this will be undefined. So this will be undefined everywhere y is 0, which is along your x-axis. Anywhere x is 0, except when y is also 0, you will have a slope of 0. So you can throw a bunch of values up there really quickly without actually having to plug in every value. So that is one way to check those out quickly. Now, this is the second to last thing I'll say is, are you matching your slopes or are you matching the original functions? So one of the things to remember is that dy dx are your slopes. And so if you're looking at this, when you think about output values of dy dx, those should be the slopes. But the actual graphs will look like the original curve. And the helpful part of this is that if something was not separable, you could figure out what the original curve looked like without actually trying to solve for y. So remember when we started back at the beginning of this live stream, we said let's look at the original function. The slope field is going to give me what those family of original functions would have looked like, right? So the slope field will look like your original function, but the outputs will be the actual slopes. So if you have that dy dx equals sine xy, you should be thinking about the fact that your original function would have been something to do with cos, right? Cos of whatever. But your original function would have had something to do with cosine, and actually probably negative cosine, because the derivative of negative cos is positive sine. So when I look at this and I see that, okay, this flattens out here, and then it's going sort of up and back down, I have a good feeling that this actually matches with that one based on what the original graph looks like. Now, same thing for this one. If you're saying that dy dx is equal to cos, then y was probably something to do with sine, because the derivative of sine is cosine. And so it makes more sense here that this would not have a slope of 0 at your y-intercept, and that this would kind of go like that. That looks more like a sine function. Now, the other way you could figure that out is to plug in some points and see what happens. So let's say we plug in points anywhere along the y-axis. So I'm looking at this line right here. Anywhere along the y-axis, this input will be 0, right? Because you'll be having your x value is 0. And sine of 0 is 0. So when you look at this, your slopes anywhere along this should be 0. And so it should make sense that that's true. Versus that does not happen on this one where your slopes are positive. Again, let's think about that this way. This one, cosine of 0 is 1. So anywhere that x is 0, you should pretty much have a slope of 1. So remember to look at, are you matching to the original or are you matching to the slopes? And that's something to really closely think about. So let's just do a couple and then we'll call it a day. This was a really quick little slope fields review. So the last tip I would give you guys is when in doubt, draw it out. Pick some points, plug them in, see what actually works. So let's match some slope fields to their original functions. So here I'm given the slope fields, and so, I'm given the derivatives. And so what I'm looking at here is trying to match up the slopes. Versus on the next one, I'm going to be given the original functions. And so then what I'll look up more is trying to match the shapes of them. So I'm looking at the slopes, and let's start with looking at what these depend on. So I'm going to start with that. So I see that 15 only depends on x, 16 only depends on y. The other two depend on both. So I'm going to start with that. So if I could find one that only depends on x, only depends on y, that would be helpful. So I'm going to start looking at some rows of things. So let's say that I look at this one. If I go across, I see that at every x value that changes, and at every y value that changes. So that's going to depend on both of the variables. If I look at b, at every y value, it is the same, and at every x value, it changes. So this one only depends on x. So I can already tell you that since this one only depends on the x value, this one should match with 15 because it only depends on what the x value is there. Now, if you took an antiderivative of 15, since it's linear, the antiderivative would be quadratic, and then that makes a little bit more sense. Now, let's go the same way on C and D. So if I look at C, it changes at every x value, and it changes at every y value, so that is dependent on both. And if we look at D, at every x value, it's the same, but at every y value, it changes. So this only depends on the y values. And so I can tell you already that this should match with 16. Now let's look at A and C. Let's think about these. So now I'm going to start thinking about either quadrants or isoclines. 17 is kind of jumping out at me about isoclines because I can see pretty easily where that would equal 0. So here, x minus y would equal 0 whenever y equals x. Versus this one, 18, would equal 0 whenever x equals 0 and y does not equal 0. So let's look for those isoclines. So x equals 0, that would be anywhere along my y-axis, except at where y is 0. So I can already tell you that this matches with 18. And that leaves 17 with this one, but that should make sense because its nullcline is along y equals x. Now, the other way I want to really think about 18 is in relation to quadrants. So you've got negative x over y. So if you think about this, negative x over y, in the first quadrant you would have negative over a negative, which would be positive. So it should be negative in that quadrant. In the second quadrant you would have negative and then negative over a positive, so your slope should be positive in that quadrant. Third quadrant is the same as the first quadrant. You have positive times a negative, so that's negative. And in the fourth quadrant, it's the same as the second quadrant. It would be positive in that quadrant. So that helps me match up with this because notice these slopes are all negative, these slopes are all negative, these slopes are all positive, those slopes are all positive. So another good way to match it up. All right. And then lastly, let's match some slope fields to their original equations. So I am now looking for what the original function looked like. So I'm looking not for what the actual slope is there, but I'm looking for what the function looked like. So let's start with some more simple ones. Y equals 1. So that's going to be a constant. It should have a slope of 0. And so when I look at that, I know that that immediately should match with D because that's the one where it's just a constant, the slope is 0, and that's that matchup. So that's that one. Now, let's look at the next one. Y equals x. So this should look like y equals x, right? Everywhere along it. There might be a different constant, but I see that pattern in H where it actually looks like y equals x, and so that would be H. So we've used that. Now, 9y equals x squared, so your original function should look like y equals x squared. It should be a parabola. It should be facing up. And so that would be in C. Now for 10, we've got 16x cubed. So this should be a cubic function, which again looks like that. And so for a cubic function, we are kind of looking for it to have this general shape. So that would be F. okay? Now, 11, it's 1 over x squared. That's sort of hyperbolic in nature. We know that our outputs should always be positive, so this is really going to look something like that. If you're not sure what that looks like, you could plug in points, but I will tell you that will match up with A. And if you weren't sure, again, you could always skip it and come back to it. Or you could take the derivative of it and then match up some slopes. Now, sine versus cosine, let's see which one makes more sense. So sine should start from its midline and then go up. And I'm going to guess I'm choosing between B and E. And I will tell you that E is the one that looks like it's the shape of a sine curve starting from its midline and then going up, versus B starts from its maximum and then goes down. So E is going to be my sine curve, B is going to be my cosine curve, and ln absolute value of x, well, ln of x looks like that. And so let's see what that matches it with. That should be G. So it's kind of a crash course on slope fields, making them, matching them, and deciding whether you're looking at the original function or the slopes. If you guys still have questions on these, let me know. I hope you have a wonderful week. Next live stream will be next Friday or Thursday night. And until then, I hope you guys have a great week. Bye.